Okay, so we're looking now at section 2.7, applications to computer graphics. Okay, applications to computer graphics. And let me just highlight this here for you. So it's a little dated, but well, what I mean is like, okay, computer graphics, what are they? They're images displayed or animated on a computer screen. Applications of computer graphics are widespread and growing rapidly. So now this book, I think it was it was originally written back, in the like early 2000s, that sort of thing. So now we see computer graphics all over the place on our cell phones and everything. Computer-aided design, CAD, is an integral part of many engineering processes, such as aircraft design, and they talk about that in the chapter introduction. The entertainment industry has made the most spectacular use of computer graphics, from special effects in Spider-Man 2 to PlayStation 4 and Xbox One. Now, just out of curiosity, Xbox, are we on an Xbox 3? How many, I mean, they keep remodeling these, right? They keep updating these Xboxes and PlayStations. We're on Xbox 10, Jonathan. PlayStation 5. Okay, all right. Well, but it's still true. So most interactive computer and software for business and industry makes use of computer graphics in screen displays and for other functions, such as graphical display of data, desktop publishing, and slide production. Okay, so consequently, anyone studying a computer language, hold on here. Hold on, where's my screen? Yeah, anyone studying a computer language would need to be familiar with 2D graphics. Now, what is this section examine? Okay, what is this section about? Okay, so let me just highlight that and take this off. I mean, it's good to see where things are used. So this section examines some of the basic math used to manipulate and display graphical images, such as the wireframe model of an airplane. Such an image consists of a number of points connecting lines or curves and information about how to fill in closed regions. Okay, so let's take a look at example one. Let's take a look at an example one here. The book has some nice examples. We'll look at a few of our own. Okay, example one. So the capital letter N. The capital letter N in figure one is determined by 8 points or vertices. Okay, so the coordinates of the points can be stored in a data matrix D. So, how does a computer understand the capital letter N? Well, one way is to place coordinates at the vertices of this capital letter N in figure one on the left. Okay, so you see there, the first vertex has the coordinate 0, 0, x coordinate 0, y coordinate 0. The second coordinate, or I should say vertex 2, well, that's just to the right of vertex 1. So its x coordinate is a half in this case, but the y coordinate is still 0. But then you can move up to vertex 2. So what I'm saying is, you see what I'm talking about are these, these vertices here, right? That's what I'm addressing. So vertex 3 is moved up from vertex 2. So the x coordinate stays 0.5, and then you're moving up a distance of 6.42 in this case. So you can represent the vertices of this letter N by this matrix D in example 1. Okay, and are there any questions on that? Okay, all right. Well, now we may want to do some animation on this letter N. For instance, we might want it to become slanted. We might want it to become slanted. So how could we do that? Well, we can multiply, like shearing. That's right, Mikhail. Shearing the sheet. We're going to slant this N, but in order for it to slant, some of the coordinates have to be moved. They have to be transformed. Okay, so right now this letter N in figure 1 is not slanted at all. If we want to transform the coordinates, we have to multiply by a 2 by 2 matrix on each coordinate. Okay, and so what would that look like? Well, let's go down here a little bit. Okay, we get to example 2. So example 2 here says, okay, let's suppose we have a matrix A that is given as first row 1.25 and second row 0 and 1. Describe the effect of the shear transformation on the letter N. Well, what they do is in the solution, what they do is they multiply the matrix A by the matrix D. That's what they do. And then you get these vertices here. Now, some of the vertices didn't change. So, like which vertices were unaffected by this transformation? Which vertices didn't change? Well, let me ask, do the vertices on the bottom, that's right, Mikhail, vertices 1, 2, and 4. And if you notice, those vertices are the same. And of course, it's because the second coordinate, the y coordinate for those vertices is 0. But all the other coordinates now are transformed into new coordinates. And in figure 2 on the left, the slanted N has the vertices that are part of the matrix product A times D. That's the effect of the transformation. So you can create animation, computer animation, through matrices. Just have the data points stored in a matrix, like a matrix D, and then multiply that matrix D by a particular matrix A that will, and that you design the matrix A so that it will do what you want it to do. Okay, now another thing in example, well, are there any questions on example 2? Okay, well let's proceed on then. Let's proceed on to example 3. So in example 3 now, in example 3, they're asking you to do 2 transformations. Compute the matrix of the transformation that first performs a shear transformation, as in example 2, and then scales all x coordinates by a factor of 0.75. Okay, so if you look at figure 2, okay, and figure 3, so figure 2, that letter N is slanted, and figure 3, that letter N is also slanted. But which letter is thinner? The letter N in figure 2 or the letter N in figure 3? That's right, Jonathan, figure 3. So effectively, it's like you're taking the x coordinates and bringing them closer to the origin. You're shrinking the x coordinates towards the origin. effectively. You're making the x coordinates smaller, and that's going to effectively cause the letter n to be thinner, and it is thinner. So what matrix would do that? Well, the matrix that multiplies the x coordinate by 0.75. So now the matrix of the composite transformation is the product of two matrices. Okay, so it's like you're doing two things at one time. If we look here in this composite transformation, if we look there, what's being done first? The scale, I want to say it the right way. Sorry. The bending, the slanting of the letter N, or the shrinking of the x coordinates. In example 3, what technically is being done first to the coordinates of the letter N? Is it the slanting of the letter N or the shrinking of the x coordinates? Let's look at this. So what acts on the matrix D first? Is it the matrix points with entries 0.750, or 1, or is it the matrix with entries 1, 0.25, 0, 1, 1? Which matrix acts on the coordinates first? Let me go to the whiteboard. Hold on. All right, let me show you what I'm talking about. So hold on here. Let me move this over a little bit. Okay, so this relates to example 3, section 2.7. Okay. Vertices, so you got vertex 1, 2, 3. Hold on. Okay, these are vertices for that letter N. Okay. Hold on. This isn't quite right. Hold on. All right, so okay, and there were 8 vertices, right? 8 vertices. And this here was matrix D. Now, what you're doing to D, what you're doing to the coordinates in matrix D is you're going to do transformation. In example 3, this is the first transformation. Okay, that's the first transformation, and this they call A. They call this A, and this is the shear transformation. It's a 2 by 2 vector acting on every set of coordinates, right? Because remember, matrix multiplication, if you go A times D, right? A times D is the same as A times the column vectors of D. If you think about matrix multiplication, there are 8 column vectors of D. And so this is equal to A times D1, A times D2. So all the columns, okay? So it's transforming the column, the matrix A, when you multiply it by the matrix D, you're essentially transforming you are transforming the vertices of the matrix D, because that's how matrix multiplication is defined, right? But if you wanted to do then another transformation, you see, you could multiply by another matrix. So the first matrix here, you did a shear transformation. But now what you want to do is a scaling transformation. So this is the matrix that does the that scales the x coordinates. That scales the x coordinates. By a factor of 0.75. So you see, because you have an S times an A here, this is called a composite transformation. You're doing 2 transformations. And even though effectively the shear transformation comes first, because of a computer, how fast computers are, you've effectively, right, looks like the letter N is bending and shrinking at the same time. You see what I'm saying? It likely would look that way to your eyes. Let's see, David says, wouldn't you need to? No, good question, David. So I have S times A times D. S is a 2 by 2, A is a 2 by 2, and D is a 2 by 8. So you got a match here. You have a match here. So the dimensions on S times A times D, S times A times D, is an 8 by 8. Right, but if you tried to do D times A times S, well, D is an 8 by 8, A is a 2 by 2, S is a 2 by 2. It's undefined, right? Because you have this column number doesn't match this number of rows. So you see, David, that wouldn't work. The matrix transformation is, remember, the matrix transformation is A times X. Remember the notation. This is just beside the point, but transformation of x equals a times x. How many recall that from earlier homework, seeing that? Yeah, Mikhail recalls it, Marcella recalls it, and you're always left multiplying a vector by the matrix A. It's just in this case, we're left multiplying 8 vectors by the matrix A. And that gets you 8 transformed XY coordinates. Okay. Are there any questions on that? So, yeah. Well, what order you multiply in depends on what you want to do first. In this case, Mikhail, we're doing the shear transformation first, and then we're scaling by the x coordinates. That's your composite transformation. So the shear transformation does come first, followed by scaling of the x coordinates. But the naked eye might not be able to see that because the computer, it acts quickly, right? The graphics are quick. Okay. Well, technically speaking, they would both work, Mikhail, but technically speaking, we want to try to think about the order of things. The thing is, you see, it wouldn't, your question's a good one. What Mikhail's saying is, you could do S times AD, or you could do S times A times D. And actually, that's an interesting point, because if you do S times A, you're getting a 2x2 matrix that'll give you the composite transformation, and then multiply it by D, and you get the composite transformation, like instantly. So, whereas if you do S times A times D, you're doing like one transformation at a time. It doesn't really matter which, but generally we do one transformation at a time. Good question. Now, another thing too we have to consider here is, what else do you see in graphics? I mean, up to now, what you've seen is you have rotations, you can shrink an object, you can expand an object, you can make it larger, you can rotate an object, you can reflect an object about an axis. But there is one operation that you have not been able to do yet with 2x2 matrices as transformation matrices. And that is translations. Have you noticed that? You've not done, yeah, well, and of course translations are important, because you want to move the object around the screen, right? You want to move the object like a Pac-Man. Think of like Pac-Man. You all know that game, right? Where the little Blinky or whatever it is moves around the screen, and the ghosts try to gobble up the. Right. All of our options, as Mikhail says, are connected to, all the objects are located at the origin. But suppose you want to move the object around. Okay, like a video game Pac-Man. You're moving the little, I don't know what's called, the Pac-Man or Pac-Woman around and being chased by the ghosts, right? Well, you got to have translations. But the problem is you can't have translations with the 2x2 matrix. You have to have a 3x3 matrix. Let me show you that. So we use, this is example 4. We have to represent hold on here. Yeah, so in this example 4, they're talking about how do you do a translation? How do you do a translation? So let me see if maybe I can help you see it. I can help you see it. Let me go to the board here. Clear that. Okay. So, all right. Let's say that hold on here. Let's say that you had an object at coordinates -2 and 2. That's your xy coordinate. And you want to transform that so that coordinate gets moved to the coordinate, hold on here, 2, 5. Well, there's no 2 by 2 matrix that's going to do that. There's no 2 by 2 matrix that's gonna give you this transform vector. So you know, here's your vector x. I want to be a little careful here how I'm saying this. What I'm trying to do is, if we go back to the book, okay, you see there the picture there on the left where they have a triangle located at coordinates -2, 2, and they want to translate that triangle 4 units by 4, 3. So 4 units to the right and 3 up. So you see how the black triangle moves 4 units to the right, and then you got the gray triangle there at 2, 2, and then you move the gray triangle up 3 units to get to the blue triangle, which is at coordinates xy coordinates 2 and 5. Okay. You want a matrix that's gonna cause that translation, and a 2 by 2 matrix will not do it. It will not do it. Another way to think about it, if I go back to the whiteboard, let's think of it like this. Let's think of it like this. Let's stick with it like this. No. Let me do this another way. Hold on. Let me do this another way. So here's some xy point, and you want x to be moved 4 units to the right, and you want y to be moved 3 units up. That's called a translation. That's a translation by 4, 3. Well, does it make sense that no matter what entries you put in here in this 2 by 2 matrix, that there's just no way you could get that vector? Does that make sense? Because yeah, there's no way you would get it. Okay, David agrees. No way. So what you have to do is you have to use what's called a homogeneous coordinates. Homogeneous coordinate. So long, Mikhail, as you don't do translations, 2x2 matrices will work fine. But for this kind of situation, it will not. So what you have to do is you represent the coordinate in two-dimensional space by the vector x, y, and 1. X, y, and 1. The 1 is, this is called a homogeneous coordinate. Now, this is a 3x1, so you're going to have to use multiply by 3x3. And what happens is here, you can just leave, I mean, you have 9 entries, but in this top left-hand corner, you just keep the identity matrix there. Okay. Where would the 4 go? So what's going to happen is we're going to do multiply, and we're going to get x plus 4, y plus 3, and 1. So the 1 in the last entry there is just kind of like a placeholder. Okay. Where would the 4 and the 3 have to go? Where would the 4 have to go? Can somebody maybe put a circle where the 4 would go? Good, good, thank you. So the 4 is going to go here. And what about the 3? Where would the 3 go? That's right, the 3 would go there. Very good. And then what are we going to have? What are we going to have here? What's going to be in this spot? Going to have zeros here. Well, you have a 1 here. A 1. That's right, Cameron, a 1. So you see, now what we can do is we can do all the transformations that we did in two-dimensional with two-dimensional coordinates using the 2x2 matrices. It's just we're going to make the 2x2 matrices. We're going to represent them as 3x3 matrices. Okay. And if we do that, then we can also include translations in our repertoire of transformations. Okay, so we use homogeneous coordinates. Well, we don't want to change the bottom row, Mikhail, because we want there to be a 1 here. We want there to be a 1 there. So the bottom row is always going to be 0, 0, 1. Where things are going to change is in this spot here, which is reserved for translations, and then this 2x2 matrix here, which will do the other types of transformations, rotations, reflections about axes, and so forth. So let's look at an example. I'd like to do one example before we go on break with this. Let me see here. Let me go here. But actually, let me just go back to the book real quick. Whoops, hold on. So I hope this makes sense then, what they're doing there in example 4. Let me see. Our previous 2 by 2 matrices, that's correct, Mikhail, would be equivalent to 3 by 3 matrices where, well, I'll tell you, let's look at an example. Let's look at an example. So now, let me bring that up. Hold on, that's not it. One moment. Okay, let you copy this example down, okay? Take a moment. Okay, so hold on here, you're copying. Well, you know, Mikhail, when I said X and Y, I could mean X1 and X2, but it seems that they are using X and Y coordinates in their notation for section 2.7. And let's see, in this problem, okay, what do we want to do here? So we want to find a 3 by 3 matrix that transforms a two-dimensional figure by shrinking it first by 70 degrees, okay, then rotating it counterclockwise 90 degrees about the origin, and then finally shifting it a half unit to the left and 2 units upward. Yeah, yeah, Mikhail. Well, the reason we can use X, Y, Z in section 2.7 is because we are working physically in either 2-dimensional or 3-dimensional space. We don't have 4-dimensional space, or so that's why. That's why. So this composite transformation involves how many transformations are involved in this composite, this multiple transformation. There are 3. That's right. So let me just ask you, the first transformation, okay, deals with the shrinking coordinates by 70%. Okay, so if you wanted to shrink coordinates by 70%, okay, and you wanted to use homogeneous, you know, again, now we're talking using homogeneous coordinates. Hold on, something's going crazy here with my pen. Hold on, let me get this crazy pen. Let's do this again. Hold on here, come on. I'm going to focus on shrinking by 70%. So X, Y, and 1. The transform coordinate, if you're shrinking an object by 70%, what would the scaling factor have to be? In other words, think of, think of the xy. If you shrink xy by 70%, what does x become? What must you multiply x by to shrink an x coordinate 70%? Take the number 10. Right, that's right, Cameron. Good. Like the number 10. If you shrink it by 70%, what is that equal to? The number 10 shrunken by 70%. That would equal 3. So think of taking 0.3 and multiplying it by x. So this is like the transformed coordinate. Okay. What about the y? What's going to be where the y is? What do we want to transform the y coordinate into if we're shrinking by 70%? What's going to go here? That's right. Good, Cameron. 0.3y. Now we're not shrinking in one direction or another direction. We're shrinking everywhere. So, and then the 1 stays here. The reason I do this is because, you see, we have a, we're taking a 3x1 vector. We're getting another 3x1 vector. So we need to multiply the 3x1 vector by some matrix A. So can you figure out what the values are going to need to be on this? Well, is there any shifting going on? Is there any shifting? And by the way, the bottom here is going to be 0, 0, 1, right? Is there any translating going on here for the first, I'm talking just the first transformation. Is there any translating going on? If we shrink an object, is there any moving of the object? No. So translation is equal to what? If we had to put in a value for the translations, right, zeros right there. Okay. Now we got to figure out what goes in these 4 spots. So what is going to go there? Well, to get this vector here, what 2x2 matrix would you need? We're kind of working backwards, right? We have the vector we want, and right, it would be 0.3, 0, and 0, and 0.3. Okay, so that's one way to think about how to get the 3x3 matrix. Another way, of course, is to say, well, there are different ways to think about it. But remember, let me see if I go back one moment here. One moment. Hold on here. Just give me a moment. Hold on. I want to close this for a moment. Get the text back. Hold on. There's something I want to bring up here. I'm going back to section 1.9. Just give me a moment. Let me get there. Wait. Hold on. Okay, let me just bring up the ebook. So if you recall, in section 1.9, you learn how to construct by theorem 10. Let me just make sure. Hold on here. Yeah, this is it. You learn how to construct a transformation matrix, say, by taking the unit vectors, E1, E2, E3, up to En, and if you could figure out under the transformation what those transform vectors were, you could also come up with your matrix. That's theorem 10, section 1.9. So if we go back to the problem here, we go back to the problem, and it's nice now, the new Blackboard, it keeps the writing that you know that you did. So like the vector 1, 0, which is E1, I knew that's E1. The transformation of E1, if you were to shrink by 70%, would be 0.3 and 0. And that's what we have here. That's the transformation of E1. So, and then the second column gives us the transformation of E2. So let me go to the next page here. I have this written more formally. Oh, come on, don't do that. Yeah. So, I mean, there are two ways to get the matrix A. Okay, two ways. How many kind of like looking at the so again, here we are. First we're going to find the matrix that shrinks the coordinates by 70%. How many kind of like writing down the transform coordinate and then based off of that figuring the matrix A? How many kind of like that approach? It's one approach. Okay, how many? Okay, Jonathan says he doesn't mind it. Okay, that's good. How many, on the other hand, like to just, well, that's right, Mikhail. And the reason I did this is so you could just appreciate the 3x3 matrix. If you were to use theorem 10 from section 1.9, in the top left, that 2x2 matrix, you would just write the transform vectors. You know, so 1, 0 would get transformed to 0.30 under a shrinking of 70%, and 0,1 would get transformed into a transform vector of 0.3 under a shrinking of 70%. And that's, Next, what we want to do is we want to find a matrix that will rotate points 90 degrees counterclockwise about the origin. So that matrix, it turns out, is going to be this matrix here. Okay, so I mean, if 0,1 gets, no, if the vector 1, 0 gets transformed to 0,1, okay, pictorially, right? 1, 0's here. Okay, that's your E1. And if it gets transformed to this vector here, then you're doing a -90 counterclockwise about the origin, you see? So that's why you have the 0,1 here. And similarly, the E2 vector, okay, the E2 vector, I'll draw another little picture here. Okay, the E2 vector, which is here. Okay. -90 degrees counterclockwise would cause that E2 vector, it would be transformed to this vector here, which is vector -1, 0. Okay, does that ring a bell? Does that bring up section? Okay. So I'm justifying to you how we got this matrix B for the second step. How many find these little pictures helpful? Are these little pictures helpful? Okay, wonderful, wonderful, good. Thank you, Mikhail, Cameron, and Jonathan. Let me see, question. Mikhail, I'd have to get back to you on that. I don't think so quickly. I want to be careful. Sometimes I just say, yeah, sure, but I don't do that anymore. I'd have to think about it. I've never seen a transformation like that, because generally we want our transformation to be invertible, our transformation matrix, and that matrix you're writing wouldn't be invertible. So I'd have to look at that. But okay, here now, here's the matrix that shifts 5 half unit to the left and 2 units up. Right, Mikhail. And so this is where, so now, you just have the identity here in the top left-hand corner. And then there's your, they call it the H and the K, right? The H and the K. There's H, there's K. And, now you multiply the three together, and the 3 by 3 matrix for the composition would be C times B times A. And what that does is this would be the transformed coordinates, transformed X and Y coordinates through this composition of the three transformations. And again, I just put this here for a reference. I certainly find it helpful. When I studied linear algebra, we didn't do this kind of thing. To my recall, I don't recall doing these kind of, well, I want to be a little careful. I think we did transformations, but now with computers and stuff, you can do more of this kind of stuff. So now let me ask you, would CBA, okay, if we had instead ABC, if we had ABC, would that do the same? Would the end product be the same transform coordinates if we did ABC? If we did C first, B second, and A third, would that give us the same result as doing A first, B second, and C third? Or does order matter here? Does order matter? I mean, let me ask you this: if it were the same, if doing the transformations in the order of C first, B second, and A first were equivalent to doing A first, B second, and C, sorry, if we did C first, that transformation, B second, and A third, if that were the same as doing transformation A first, B second, and C third, effectively we'd be saying ABC equals CBA. But is A times B times C equal to B, C times B times A? Is that generally true? No. Matrix multiplication is not commutative, right? It is not commutative. So if you do the transformations in a different order, you're going to get a different looking figure. And so now the final answer then, if we multiply C times B times A, and you can work it out by hand, it's not a problem, but you can use MATLAB to do C times B times A. Hold on. This would be your result. And that will be the 3 by 3 matrix for that composite transformation. So if you had a two-dimensional figure or character in like a cartoon character or something, or a video game character, and you represented that video character with a bunch of data points, this transformation on those data points would cause the character to shrink by 70%, turn counterclockwise 90% about the origin, and then do the shifting of a half unit to the left and 2 units upward. I'll show you this in example 6 actually. See figure in example 6. So I'm going to show you that figure, and then we'll take our break in a few moments. Are there any questions so far? Yeah, yeah. All right, let me find this in the book here. Hold on. One moment here. Find it here. Yeah, I'm not. I mean, I have to think more carefully what it does. But I guess Mikhail's saying what he's discovering there. Um, if you did the, so hold on here. Let me just move this down a little bit. Go down a little bit there. Hold on, I'm gonna have to make the print a little smaller so that you all can see it. No, I gotta make it smaller. I want it to show for you. One moment. Okay, so this is what happened. So we did example 6. Okay, we did example 6, and there's the original figure. In the second picture, what does the figure seem to be doing? That triangle to the left, triangle, is it getting bigger or smaller after the scaling or the shrinking? The original figure, the triangle on the left there, example 6, this is what we did, this exact problem just now. So on the left here, you have that blue triangle, original figure. After the scaling, what happened to the triangle? Did it shrink or expand? It shrunk. That's right, Jonathan. That's right, Marcella. By how much? How much does it look like it shrunk by? What percent? Okay, Jonathan says 3/4, or about 75%. In fact, Jonathan, it's 70%. Okay, because again, this example 6 is what we just did and you did in your notes. 70%. That's okay. That's all right. Now, then there's a rotation. How many degrees is the triangle being rotated? "90 degrees. Good, Marcella. Good, Jonathan. Is it clockwise or counterclockwise? Counterclockwise. Good. Okay, and then finally, okay, Mikhail, in the last picture, after translating, how does the figure move? Well, it seems to move, does it move to the left or to the right? So after the translating, does the figure move to the left or to the right? It moves to the left. That's right. That's that negative 0.5, right? That when it's a negative 0.5 translation, you're moving to the left for the x coordinate. For the y coordinate, it's 2, so you move up 2. So are there any questions on this? Any questions at all? How many think honestly this is a pretty cool stuff? Pretty cool section here. Okay, Mikhail's liking it. Okay, Cameron likes it. The math's a little difficult, he says, but he likes it. Yeah, absolutely, Jonathan. And you know what would be even cooler than two-dimensional graphics? We're going to look at some three-dimensional graphics. We're going to look at that next. So I'll stop the lecture here. And if are there any questions before I stop the lecture? All right. Oh, you'll be fine, Jonathan. Don't worry. We have theorem 10 from section 1.9 to help us. Yeah. Well, Mikhail, now you know how these 3D how these graphics are, how they're generated. You know, and a lot of math. Okay, I'll stop the recording. Thank you.